10.5 Densities of gases. If we divide both sides of the ideal gas equation by volume and the constant R and T, we get this adaptation of PV equals nRT. We know that moles times molecular mass equals mass, or moles times grams per mole would equal moles. So multiplying both sides by the molecular mass would give us M over V equals pressure times molar mass divided by RT. We know that mass divided by volume equals density, so we can manipulate the equation even further and say that density is P times molar mass over RT. We only need to know the molar mass, the pressure, and the temperature to calculate the density of a gas. So this equation you will find to be very useful. Again, density equals pressure times molar mass divided by RT. Molecular mass. One can manipulate the density equation to enable us to find the molecular mass of a gas. So again, we're looking at the same equation, and if we manipulate it a little bit, we can turn that into molar mass equals density times the constant R times T over P. So same equation, just solving for a different variable. Let's apply that equation to sample exercise 10.7, calculating gas density. So our question is, what is the density of carbon tetrachloride vapor at 714 torr and 125 degrees Celsius? And again, we only need to know the molar mass, the pressure, and the temperature to calculate the density of a gas. So the temperature on the Kelvin scale is 125 plus 273, or 398 Kelvin. The pressure in atmospheres is equal to 0.939, so we converted 714 torr into atmospheres. And the molar mass of carbon tetrachloride, or CCl4, is 154 grams per mole. So again, we're using density equals pressure times molar mass divided by the gas law constant R, and temperature has to be in Kelvin. So again, anytime you're doing calculations, make sure that your units are canceling out. Make sure that you're using the right gas law constant. So in this case, I can see that my atmospheres will cancel out, my moles will cancel, my kelvins will cancel, and the only thing left is going to be grams per liter, which is perfect because density is mass divided by volume, grams divided by liters. That makes sense. Please practice. The mean molar mass of the atmosphere at the surface of Titan, Saturn's largest moon, is 28.6 grams per mole. The surface temperature is 95 Kelvin and the pressure is 1.6 atmospheres. Assuming ideal behavior, calculate the density of Titan's atmosphere. Okay, sample exercise 10.8, we are going to calculate the molar mass of a gas. So, same basic equation, we're just going to manipulate it a little bit to figure this out. A series of measurements are made to determine the molar mass of an unknown gas. First, a large flask is evacuated and found to weigh 134.567 grams. It is then filled with the gas to a pressure of 735 torr at 31 degrees Celsius and reweighed. Its mass is now 137.456 grams. I hope you see where they're going with this already. They've given you the pressure, they've given you the temperature, and by subtraction, we can find the mass of the gas. Finally, the flask is filled with water at 31 degrees Celsius and found to weigh 1,067.9 grams. The density of the water at this temperature is 0.997 grams per milliliter. Assume that the ideal gas equation applies and then calculate the molar mass of the unknown gas. So we're given the temperature, 31 degrees Celsius, and the pressure, 735 torr for a gas. Together with information to determine its volume and its mass, we are asked to calculate its molar mass. We need to use the mass information given to calculate the volume of the container and the mass of the gas within it. From this, we can then calculate the density of the gas and then apply equation 10.11 to calculate the molar mass. So the mass of the gas is the difference between the mass of the flask filled with the gas and then when it's empty. So the first weight is 137.456. That is the flask with the gas in it. And the second mass, 134.567, is the completely evacuated flask. There's nothing in it. So the mass of our gas is 2.889 grams. The volume of the flask, or the volume of the gas, will equal the volume of water that's in the flask, because a gas will take the shape of its container. So the volume of gas is the volume of the container. It told us that the volume of water is calculated from mass and density. So they filled up the flask with water and they figured out how much the mass of the water was. The mass of the water is the difference between the masses of the flask full and the masses of the flask empty. So why would we do this instead of just saying that we put it into a 500 milliliter flask? Because we want to get a good number. We want to get a really good number for the volume of that gas. So again, 1,067.9 grams is the mass of the flask filled with water, and 134.567 is the mass of the flask completely empty. So our water's mass is 933.3 grams. We know that the density of water is 0.997 grams per milliliter. So by dividing the mass of the water by the density of the water, we found out the volume of the flask with a very good precision, 936 milliliters or 0.936 liters. Knowing the mass of the gas, 2.889 grams, and its volume, 936 milliliters, we can then calculate the density of the gas, mass divided by volume, or 3.09 grams per liter. We're going to be using the equation molar mass equals density times R times T over P. So we just figured out that the density of the gas is 3.09 grams per liter. We're using the gas law constant 0.0821 liter atmospheres per mole Kelvin. Notice that my units are all in agreement and they're going to be canceling out. The temperature was 304 Kelvin, and our pressure, we're converting pressure to atmospheres and temperature to Kelvin. Okay, so in the bottom, in the denominator of this equation, we are converting torr to atmospheres by dividing by 760. You'll remember that 760 torr is equal to 1 atmosphere. So they're just doing a little conversion in the denominator there. All of the units will then cancel out, and we will find that the molar mass of the gas is 79.7 grams per mole. Okay, practice exercise. Calculate the average molar mass of dry air if it has a density of 1.17 grams per liter at 21 degrees Celsius and 740 torr. Sample exercise 10.9, relating the volume of a gas to the amount of another substance in a reaction. The safety airbags in automobiles are inflated by nitrogen gas generated by the rapid decomposition of sodium azide. If an airbag has a volume of 36 liters and is to be filled with nitrogen gas at a pressure of 1.15 atmospheres at a temperature of 26 degrees Celsius, how many grams of sodium azide must be decomposed? This is pretty crucial if we want an airbag to work properly and save lives. This is a multi-step problem. We're given the volume, pressure, and temperature of the nitrogen gas and the chemical equation for the reaction by which the nitrogen is generated. We must use this information to calculate the number of grams of sodium azide needed to obtain the necessary nitrogen. We need to use the gas data, pressure, volume, and temperature, and the ideal gas equation to calculate the number of moles of nitrogen gas that should be formed for the airbag to operate correctly. We can then use the balanced equation to determine the number of moles of sodium azide, and then finally we can convert the moles of sodium azide to grams. The number of moles of nitrogen is determined using the ideal gas equation, PV equals nRT. So we're going to plug in our numbers for pressure, volume, and temperature and calculate that we are going to produce 1.7 moles of nitrogen gas. From here, we use the coefficients in the balanced chemical equation to calculate the number of moles of sodium azide. We see that the moles of sodium azide to moles of nitrogen is a 2 to 3 molar ratio, which again we get from the coefficients in a balanced chemical equation. And here we're just converting moles of nitrogen to moles of sodium azide, which is 1.1 moles of sodium azide. Finally, we're going to use the molar mass of sodium azide and convert to grams. So converting moles to grams using the molecular weight of sodium azide, we get 72 grams of sodium azide. Please do the practice exercise. In the first step in the industrial process for making nitric acid, ammonia reacts with oxygen in the presence of a suitable catalyst to form nitric oxide and water vapor. How many liters of ammonia gas at 850 degrees Celsius and 5 atmospheres are required to react with 1 mole of oxygen gas in this reaction?